Hello everyone, welcome to the lecture again. Today we will discuss about the general equation of motion of a rigid body which is moving in a plane. Let us say the forces on the rigid body is acting in the xy plane, and let us say there are many forces. So, F1, F2, F3 and F4. So, as I said that let us say the body is moving in the xy plane because the forces are acting in the xy plane. Now, we already know that the general system of forces which are acting on the rigid body, they can be replaced by a resultant force and a corresponding couple. Okay. So, let me write this down. General system of forces acting on a rigid body may be replaced by a resultant force applied at a chosen point and a corresponding couple. Okay. Now, here we have a chosen point. This chosen point is up to me which point I would like to choose. Let us say that I choose the mass center as my point. Okay. So, here chosen point is, let us say, the mass center. Okay, let me call it G. Okay. Now, the effect of these forces can be replaced by a resultant force which is passing through, let us say, G. So, we have summation F and a couple about G. So, let us say mg, and we know the equation of motion. So, summation F is going to give me ma, okay, where a is the acceleration, and the couple m is going to give me the rate of change of angular momentum. Okay. So, let us say I denote the angular momentum by h. So, it is passing through G. So, h dot G. So, here h is the angular momentum and hg is the angular momentum of the rigid body about its mass center G. Okay. So, we have two equations, one is for the translation and one is for the rotation. So, translation equation of motion, that is summation F equal to m a bar. A bar means the acceleration about the mass center. Okay. So, that means acceleration of the mass center, and we have rotation equation of motion, that is summation m g is equal to h g dot, and as I said h g dot is the rate of change of angular momentum about its mass center. Okay. Now, we know that h g dot is equal to I omega dot and this I is again about the mass center, and this can also be written as, because omega dot is alpha. So, therefore, that can be written as I bar alpha. Okay. Okay. This is the general equation of motion for a rigid body in planar motion. Okay. Now, note that to write down these equation of motion, we have taken or chosen the mass center as our point, but we can also choose some arbitrary point on the rigid body. So, let us write down the alternate moment equation for that point. Alternate moment equation. So, we have this rigid body, earlier we have taken G, now let us take point P. Okay. Now, in the previous case we saw that the equation of motion was summation F equal to ma, and then there was the moment about the mass center. So, mg. Now, let us say this point P is situated at a perpendicular distance of d from the line of action of ma, then summation mp or the moment about P will be the moment about the mass center g plus the force into perpendicular distance. So, ma into d. Okay. Now, we know that summation mg is equal to I bar alpha or h dot g. So, therefore, this equation can be written as summation m p equal to I bar alpha plus m a into d. Okay. Or we can write down summation m p equal to h g dot plus m a into d. Okay. Now, let us see when the point P is more convenient than the mass center point G. Let us say I have a rigid body, and on this rigid body force F1, F2 and F3 are acting. So, we have our mass center G, let us say over here. Now, let me extend the line of action of F1 and F3, okay, and at the intersection let me take point P. Okay. So, if we have less information about F1 and F3, in that case we can take the moment about P, because then the effect of F1 and F3 will be 0. Okay. So, if you want to eliminate F1 and F3, then the point P is more convenient. Okay. Now, based on these concepts, let us look at some of the problem. The first problem statement is following. An air table is used to study the elastic motion of flexible spacecraft model pressurized air escaping from numerous small holes in the horizontal surface provides a supporting air cushion which largely eliminate friction. The model shown consists of a cylindrical hub of radius r and 4 appendages of length L and small thickness T. The hub and the 4 appendages all have the same depth d and are constructed of the same material of density rho. Assume that the spacecraft is rigid determine the moment m which must be applied to the hub to spin the model from rest to an angular velocity omega in a time period of tau second. Now, in this question we have been asked to determine the moment m which must be applied to the hub to spin the model from rest to an angular velocity omega in period tau. Okay. So, the moment m about the z axis will be I z z into alpha, where alpha is the angular acceleration and alpha will be the angular velocity divided by time. So, it is tau. Okay. Therefore, summation mz will be I z z into omega divided by tau. Let me call this equation number 1, and the only thing that we need to determine now is I z z. Okay. So, I z z or the moment of this assembly about the z axis will be half m, let us say h for the hub and b for the blade. Okay. So, we have one hub and it is in the shape of the disc. So, therefore, the moment about the z axis will be m h r square plus there are 4 blades. So, 4 and let us say the blades are in the shape of the rod. So, that will be 1 by 12 m b, its length is L. So, L square plus this is the moment of inertia of this blade about an axis which is passing through the center. then we can use the parallel axis theorem. So, that will be mb into this distance, okay, and that is r plus L by 2 square. Okay. So, for that we have used the parallel axis theorem. Okay. Now, we can simplify this because the density is given. So, that will be half, mass will be area. So, pi r square into the depth. So, which is d into rho multiplied by r square plus 4 into mass. Mass is L d into T multiplied by rho. So, that is the mass, and then we have L square divided by 12 plus, let me extend this. So, this will be r square plus L square divided by 4 plus R L. Okay. So, this can be written as rho into d. We have r to the power 4 pi divided by 2 plus 4 L t, L to the power 3 divided by 3 plus R L plus R square. Okay. So, this is the moment of inertia about the z axis. Now, let us put this in 1. So, we get m equal to rho d omega divided by tau pi r to the power 4 divided by 2 plus 4 L t L to the power 3 divided by 3 plus R L plus R square. Okay. So, this is the moment that we have to apply to spin this model from rest to an angular velocity omega in time tau. Okay. Now, let us look at another problem statement. The pendulum has a mass of 7.5 kg with center of mass at G and has a radius of gyration about the pivot O of 295 mm. If the pendulum is released from rest at theta equal to 0 degree, determine the total force supported by the bearing at the instant when theta equal to 60 degree, and it is given that the friction in the bearing is negligible. In this question, we have been asked to determine the total force supported by the bearing at the instant when theta is equal to 60 degree. So, let us first identify all the forces that are acting on the pendulum and the pivot. So, we have this pendulum and we have the pivot at point O. So, first of all, its mass is going to act downwards, and it is given it is 7.5 kg. So, 7.5 into 9.81 Newton, and it is making an angle theta which is 60 degree. So, let me just write down this angle as theta. Okay. So, therefore, this angle will also be theta, okay. And let us take the direction along the pendulum as n, and the tangential direction in which it is moving, let us say that is t. Okay. So, we have plus n direction here and we have the t direction, okay, plus t direction. Now, since this angle is theta, okay, and this angle is 90 degree, therefore, this angle will be 90 minus theta, and therefore, this angle will be theta. Okay. Now, this pendulum is rotating about point O. So, let us say its angular velocity is omega and the angular acceleration is alpha. So, we can now write down the equation of motion in the n and the t direction. Okay. So, the force in the n direction will be, so note that about O, this is making a fixed axis rotation, and in the fixed axis rotation the force in the n direction is m r omega square. Okay. Let us identify the forces in the n direction. So, we have at O we have the reaction forces, let me mark them by red. Now, at the pivot we have the reaction forces also. So, let us say we have from O in the t direction and from O we have the force in the n direction. Now, let us balance all the forces. So, we have O n force in the n direction minus the projection of the weight along the n direction. So, that is minus 7.5 into 9.81 sin 60 degree, because theta is equal to 60 degree, equal to m r omega square. M is 7.5, r is the length of this pendulum. It is given that this is 250 mm. So, therefore, 0.25 into omega square. Okay. Let me call this equation number 1. Similarly, let us balance the force along the t direction. So, we have the equation of motion summation f t. Now, the force in the t direction is m r alpha. Okay. So, the forces are minus O t plus 7.5 into 9.81 cos 60 degree equal to 7.5 into 0.25 into alpha. Let me call this equation number 2. Now, note that the support reaction at O I can find out if I know the value of omega and alpha. Therefore, first we have to find out what is omega and alpha. Okay. Now, alpha I can find out by taking the moment about O. So, we know that summation, the moment about O will be I O into alpha, where I O is the moment of inertia about O. Okay. So, M O will be 7.5 into 9.81 into the perpendicular distance of the weight. So, that is 0.25 cos theta equal to I O. It is given that the radius of gyration is 295 mm. So, m k square equal to I naught, and k is 295 mm. So, therefore, I O will be mass 7.5 into 0.295 square and multiplied by the alpha, and this gives me alpha equal to 28.2 cos theta and if we put theta equal to 60 degree, we get the instantaneous value of alpha. Okay. Now, let us find out omega. We know that omega equal to d theta over dt, therefore, alpha is equal to d omega over dt, or omega over alpha equal to d theta over d omega, and therefore, omega d omega equal to alpha d theta. Okay. Now, the value of theta changes from 0 to pi by 3, and we know the functional form of alpha as a function of theta, it is this. So, therefore, we get omega square equal to 48.8 radian per second square, and we can put this in equation number 1 and 2. So, we get On equal to 155.2 Newton and OT equal to 10.37 Newton, and therefore, O, which is the square root of On square plus OT square, will be 155.6 Newton. Okay. Now, let us look at one more problem. Problem statement is, when the forward speed of the van is 10 meter per second, the brakes are suddenly applied, causing all 4 wheels to stop rotating. The van skids to rest in 7 meter. Determine the magnitude of the normal reaction and the friction force at each wheel as the van skids to rest. Okay. So, let us look at the free body diagram. So, we have this van okay. It has the center of mass. So, its weight is going to act downward, and at point A we will have a reaction force. So, let us say NA. Similarly, at B we have NB, and the frictional forces are going to oppose the motion. So, here we have the frictional force at A is mu k, where mu k is the kinetic friction coefficient, and NA, and similarly here we have mu b NB. Okay. Now, because of all these forces, the van is eventually going to stop and going to experience a deceleration force. So, we have G, and the force will be m a. Okay. So, it is given that the initial velocity is 10 meter per second, and it travels a distance of 7 meter before it comes to the rest. So, we can use the deceleration value V square equal to V naught square plus 2 AS, final velocity is 0, initially it is moving with a velocity of 10 meter per second. So, 10 square plus 2 into A into S. So, that gives you the acceleration A equal to minus 7.14 meter per second square, or the acceleration is 7.14 meter per second square in the opposite direction of the velocity. Now, let us look at the forces in the y direction. Okay. So, we have in the y direction there is no acceleration. So, we have summation Fy equal to m Ay, but since there is no acceleration, so that will be equal to 0. Therefore, the forces in the y direction should balance. So, we have force in the y direction Na plus Nb minus W equal to 0. Therefore, Na plus Nb should be equal to W. Let me call this equation number 1. Now, forces in the x direction, summation Fx equal to m Ax. Okay. So, therefore, minus Ma, okay, equal to, let us identify the force in the x direction, they are only the frictional forces. So, minus mu k Na plus mu k Nb. Okay, minus will get cancelled. So, I have mu k Na plus Nb, and from equation number 1, Na plus Nb is equal to W. So, therefore, this is equal to mu k W, or Ma equal to mu k, W is mg, m will get cancelled, and the value of A we already know. So, therefore, mu k will be A divided by G. A is 7.14 divided by 9.81, and that is equal to 0.728. Okay. Now, we are also asked to find out the normal reaction forces, and for that we have equation number 1, but in equation number 1 there are two unknown Na and Nb, therefore, we need one more equation, and for that we can use the moment equation. For that we have to choose a point. Okay. So, the more convenient point in this problem is either point A or point B instead of point G, okay, because in that case one of the reaction forces will go away. So, let me choose point A and then take the moment about that. Okay. So, the equation of motion is summation Ma is equal to I bar alpha plus Ma into the perpendicular distance of this force, which is this, let me call this d. Okay. So, let us take the moment about A. So, the tendency of the force W will be to rotate this in the clockwise direction. So, therefore, minus W into this distance is 1.5 meter, 1.5 plus we have Nb into the perpendicular distance is 1.5 plus 2.1, so that is 3.6 equal to I bar alpha. Okay. Note that here there is no angular acceleration, so therefore, this alpha is 0. So, therefore, we have 0 plus Ma into d, d is 1.2 meter. Okay. Now, this equation gives me Nb equal to 0.659 W. We can put this in 1, we will get Na equal to 0.341 W. Therefore, the frictional forces which are mu k Na and mu k Nb, they will be, so mu k we have determined, it is 0.728 into Na also we know, Na was 0.341 W, that is equal to 0.248 W, and mu k Nb will be 0.728 into Nb is 0.659 W. which is equal to 0.48 W, and note that there are 2 front wheels and 2 rear wheels in the van. So, therefore, the N front or the reaction force will be the half of what we have determined. So, let me just write down, since there are 2 front and 2 rear wheels, therefore, N front will be half of NB and N rear will be half of NA. Similarly, the friction force at the front will be half of mu k N B, and at the rear it will be half of mu k N A. Okay. With this, let me stop here. See you in the next class. Thank you.